Hi, I'm Cheyenne Atapour, and my project is on encrypted block size voting within Monero. So Monero is a privacy-focused blockchain that aims to preserve privacy for all participants in the ecosystem. So as this three-cup game shows, essentially what we're trying to do is hide transactions so we don't know the senders and the receivers. This property is achieved through cryptography with ring signatures and one-time addresses. So blocks are what store information on a blockchain, and in our case, transactions. The bigger block you have, the more storage space you need. So as blocks grow, you can only have the most powerful computers running the blockchain, and this can cause a problem because now the blockchain is essentially controlled by less and less people. On the flip side, you can fit more transactions on a larger block, which effectively increases the transaction speed as you're not waiting for new blocks to be mined to run your transactions. With smaller blocks, you can fit these in smaller computers, so more people can contribute to the network and leads to decentralization and more security, but you have higher fees associated with smaller blocks. These affect people that transact on the blockchain, but can also incentivize miners as they get part of that fee. So my proposal to resolve this issue of block size is, so when a miner mines a block, they will add a vote to the header. Then when this is sent to the blockchain can verify both the vote and the hash. Then once 100 blocks have been verified, we can tally up these votes. And then the result of that election will determine the new block size, whether we additively increase, decrease, or keep blocks the same. And this process, of course, will repeat. So to get there, we're going to use Palia for voter privacy. So Palia is a crypto system. Importantly, we have probabilistic encryption. So if we encrypt the same plaintext twice, it's extremely unlikely that we would get the same ciphertext. Then we also have homomorphic addition of plaintexts, which means that we can multiply ciphertext together, and that will correspond to adding the underlying plaintexts together. This will let us tally secret votes without decrypting each individual vote. So what this looks like, for example, we have a random number here that's generated for our vote, 10,000, and another 10,000 here. But the encrypted votes in both cases are different. And we only maintain this running encrypted sum, and we can just decrypt the result of the election at the very end, which in this case was to increase block size. Now, we're also going to use a non-interactive ZKP for election integrity. This will let us prove our votes are valid without revealing actual votes. The only information we learn is that our vote is within a certain set of allowed votes, and there's no other additional transfer of information. What this entails is a voter sending committed values so that anyone can verify the validity of their vote. So for example here, we have the vote 100, then the encrypted vote is this, then the voter commits these following values that any verifier can run these 4 equations and indeed say, yes, this voter voted responsibly, so we can't accept this block. So here's a demo I've created where I run my own local private testnet on my fork of Monero. So here I create a wallet. We are going to have an issue to say that there's not a node running, but we're going to resolve that in a second. We have no seed offset phrase. We're not restoring from any blockchain, and we're not enabling background mining. So now we've created that wallet. We're running up this node here, and then in the background, I'm going to be running up another node. And so we're going to see in a second, we are now synchronized with the network, so we may start commands. And so the command we're going to start to run is to mine into the wallet we just created. So there we go. We are finding new blocks at different heights, and our vote, even though this miner is always voting to increase block size, these votes are of course all different because of the property of Palia, the probabilistic encryption. So then, once we get to the 100th block mined, we can see the decrypted sum of votes was indeed a unanimous vote for increasing the block size. So the core engineering challenges I've overcome in my project were to understand a theoretical crypto system in ZKP, adapt this idea to utilize within Monero, and then actually turn this into working low-level C code. So my codebase is the only current open source implementation of this NISKIP in C. My implementation is general and applicable outside of Monero just as a general voting system. I can also flexibly import and use other crypto libraries as needed, and there's also negligible performance impact. As you saw, we only need a few integer calculations per block. In the future, my code will have to be vetted by experts, and also the community should agree upon this added feature before deployment. So as my roadmap, in my first week, I did my research. Second week, I implemented a demo scheme, as you saw the screenshots of locally. Then weeks 3 and 4, I implemented the private testnet that I had on the Monero fork. And the next step could be to Dockerize this node, run it on AWS, and provide an API to get voting and performance stats. So I've been Cheyenne Atapour. My interests are in security, cryptography, machine learning, and algorithms. I have a few hobbies here. So from card games, I learned critical thinking, forecasting, and decision-making skills. Skateboarding has taught me how to study independently and learn from failure. And being in a band has taught me teamwork and communication skills. Thank you.